All right, so I'm recording this lesson. I'm here on GeoGebra, and I am going to open a spreadsheet right here, which is going to look a little bit like Excel, basically. Okay, so I have a spreadsheet where I can put numbers. And let's say I just want to do this simple regression analysis, which goes in this direction. I ask myself the question, is sleeping many hours good for me in terms of results in school? Is it good if I sleep well, or is it not? Because it's obviously, something that should be related to performance. If I get enough hours of sleep, then I perform better in general, in sports, in school, or whatever. I'm in a better mood. So let's compare hours of sleep with performance, meaning, your mean grade that you're getting in school out of 7. So first of all, you see, well, I'm totally going to make up numbers here, but the choice of variables is important. And I'm also going to specify how I'm going to measure these variables, like what unit. Like sleep, we can measure it in hours, and your mean grade in school could be a number out of 7. So on a scale from 1 to 7. And I've specified that, not just here on the spreadsheet, but also in my exploration. If I had to do one, I would have to state this clearly. My variable X is hours of sleep. My variable Y is my mean grade out of 7. And then let's say I did a survey over some of my friends, or I surveyed all of you guys, and I collect some data. There's a person that sleeps 7 hours and has an average of 5.2, a person that sleeps 6.5 hours and has an average of 4.1, somebody has to sleep 8 hours and has an average of 3.5, somebody who sleeps like even more than, I mean, in a week on an average 8.5 hours and has an average of 6.8, and so on. And you keep collecting data, and this is what I get. And I'm just gonna throw in some numbers. It doesn't really matter. Let's do 7.5 again, and an average of 4.7. Okay, so these are my numbers. Okay, and I want to see if there's a correlation between this X and this Y variable. So what do I do? Well, first of all, I would like to plot them on a graph. So by selecting them and going here, okay, I can make it into a list of points. Okay, I'm gonna call it list 1 or whatever, or my regression. Well, let's call it list. Okay, now you don't see them because they are hidden somewhere here on the graph. We need to move this in order to see where it is. Obviously, the domain is somehow between, 4 hours and 8 hours. So these are my points. What does it look like? Can anybody tell me if you feel like there's a strong correlation, weak correlation, no correlation? Anybody? Come on, people. Don't be passive.
Medium correlation.
Like a positive one, like the more you sleep, the better you get at school, or a negative one, like the more you sleep and the worse it is? What do you think?
Oh, more positive, I think.
Positive.
I mean, we expect it to be positive, and it's good before we do the analysis if we have an idea, okay? So what do I expect from my data? Even before I plot it, I would expect like a moderately positive correlation. If I sleep well, then I perform better. Although it's obviously subjective. From what I see here from this data that I've collected, I don't know. I don't see much correlation, to be honest. Well, how do we do that? Okay, on GeoGebra, I go back to my numbers. Okay, I select them, and with this tool here, you see kind of the statistics symbol on top. We can do the 2-variable regression analysis, and it's going to open another window. Okay, and on this window, I see the graph with the regression line on it, and you see it's right here at the bottom. It's y equals 0.3914x plus 1.9947. That's the regression line. It has been calculated directly. I can also report it on my graph, so copy to graphs view. I know there's a lot of stuff here now, but you can also see it on the Cartesian plane, okay? So it looks like there is some positive correlation. Maybe I'll open it a little more so that we can see better. it looks like there is a positive correlation, but I also like how strong this correlation is. And so by clicking on this show statistic button here, I also see something similar to what you see on your calculator when you do regression analysis. As you can see, the R squared is very low. Okay, so the Pearson coefficient here is 0.4232, which is pretty low. So this is I would say a moderately weak correlation. Oh, okay, so you have found out that in this particular case, for this set of data, there is a weak correlation. It's positive, so it looks like the more you sleep. For this group of people, it is true that the more they sleep, and the better they get in school, but maybe not that much. How do we interpret this data? Well, first of all, the R number, as we know, gives me the strength of the correlation, okay? So, and we see it's weak. Then if we look at the line, the equation of the line is y equals 0.39x plus 1.99. The slope is 0.39, okay, which is positive. And what does the slope represent? Can anybody comment on the slope? I will write it here. So the slope is 0.39. The Pearson coefficient is 0.42, basically. 0.42. I think it's very important that we give some meaning to this equation, because, you know, an exploration in which you see, okay, this is what I got from GeoGebra or from Excel or whatever. This is the regression line. Who cares? Anybody can calculate that, right? I mean, if you have a computer, you know how to do this. But what do we read in it? Anybody? What is the slope representing in this case? What is this 0.39? What is the slope of a straight line? All right.
How steep it is.
What is it? How steep? Yeah.
How-
Yeah. Like qualitatively, you look at it and you see how fast it goes up. Okay. But mathematically, it's the ratio, it's the division.
Rise around.
Yeah, exactly. Rise over run. So the increase in y over the increase in x. Okay. How much y increases when x increases. So in our case, because our x is the sleep hours, and oh gosh, and no, not a good idea to write x here, because it's just gonna plot the function x, which I don't want. So let me see what it is. Well, fine, I will get rid of it. But anyway, our x variable here is the number of hours you slept, and the y variable is your grade. So it looks like from the slope, okay, for every 1 hour more that you sleep, how much better do you get in school? Okay, 1 hour sleep. That means that you get 0.39 more in your grades. So 0.4 basically, about 0.4 increase in your grade. And of course, this is subjective, but the statistics, you know, when we do statistics, we talk about the average behavior of these variables. So on average, for these people that I've surveyed, it looks like sleeping 1 hour more will increase their grade by 0.4. Okay, so this is what we find out. It's very important whenever you do regression analysis that you look at the line and you say something about the slope. Okay, that shows understanding. On your criterion E, you're going to be tested on understanding. If you don't explain what you're seeing in these terms, you're not going to get a good grade in criterion E, because you need to show that you not only do you have applied mathematics, not only have you applied mathematics, but you have also understood what you got. Okay, so the slope, and maybe I will give you some notes on this in case you decide to do linear regression. The slope represents the average increase of the y variable compared to the average increase, to the increase of 1 unit on the x variable. So imagine you increase your unit by 1 in the x variable. That's what your y variable on average increases by. So this is something that you can actually say. Another way, and this is true for, you know, what another way, yeah, we can do that. So I can introduce also like the next example. But another good way to compare, to say whether your regression is good in terms of fit, like does this line fit the points? It doesn't really look like, right? Now I'm gonna have to get rid of the orange one because seriously, we don't need that. Okay, this is your regression line on the Cartesian plane. You see that it doesn't really fit much. Well, a way to say if this is a good fit or not is that to calculate the distance between each point to the line. And how do we do that? Well, this is what we have here. If you look at GeoGebra on this side, you have the definitions of all the objects, and your line has been, you know, calculated here, and it's this function g of x. So the name of this line is g. I'm going to use it to calculate some values. Well, first of all, you can also go to your statistics here and calculate some values of the line. For example, let's say that you find out that somebody in this group sleeps for, I don't know, an average of 6.2 hours. So if you enter the value x 6.2, you're going to get the value of y. So this person technically should expect to get a mean grade of 4.42 in school. Obviously, this is just like pure interpolation. So it's, you know, trying to predict something. It doesn't really mean that for sure this person by sleeping 6.2 hours on average will have this grade, but this is just like an indication. And this is called interpolation. Interpolation is usually not too risky. Like if you take a number that is within the domain of the numbers that you have, look at my numbers. I had something between 5 and 7, basically. Well, actually, no, 5 and 8.5. So this number is within that interval, which is fine. If I choose something different, for example, let's say that I find somebody who sleeps 3.5 hours a day, okay, but obviously the line will predict something much smaller, so an average grade of 3.36. But this is extrapolation. Extrapolation means you are trying to calculate a value, you're trying to use your model to make a prediction about a value that is outside of your domain. Outside because we got a much smaller number than the numbers that I had. It's, you know, below my domain, but I could also try with something above. Let's say somebody sleeps for 10 hours. Well, this person is expected to get a 5.9. These are values that should not be used because extrapolation is dangerous in general when you do regression. Your regression analysis makes some sense within your domain, but if you go outside of your domain, it might be like dangerously wrong. Let me give you an example. Let's say somebody sleeps 15 hours. See, we get a grade that doesn't even make sense. Obviously, there is nobody probably that sleeps an average of 15 hours, and these people probably don't even go to school. But you know, that's exactly the point. If you, the further away you go from your domain, and the worse it is in terms of your modeling and your regression. So you cannot really use that information for anything serious. But if you stay within, and so you find somebody, like we said, that sleeps for 6.2 hours, then this is a reasonable expectation. I was saying that there's another way to evaluate the goodness, let's say, how well this fit is for your data, and that is try to compare the numbers that you found in the y variable, okay? How do they compare to the numbers that the line gives me? So I am going to calculate here g of 7. So for this first value, the x was 7, I'm gonna calculate g of 7. I'm not gonna write g of 7, I'm gonna write g of A2, which is the name of the cell where that number is. And that gives me 4.73. That means that the line predicts a value of 4.73 for a person that sleeps 7 hours. Now, this person gets a grade of 5.2, but my model would predict for 7.73. If I drag it down on the other values, I get other values here. Okay, and you see, obviously, your model does not really fit your data perfectly, but it goes somehow close to it or not so close to it. How do we evaluate if the model is good? Well, we take the difference between these numbers. We call it like the residuals or errors if you want. Maybe it's better to call them errors. It's not like an error that the model does. It's like a distance, let's say. And how do we calculate that? We take the absolute value, which can be calculated with the function abs, absolute value of, for example, in this case, B2, which is the true datum that I have, the true number that I got from my statistics, minus compared with C2, which is the one that I get from my model. So the true one versus the predicted one. I take the difference in absolute value. There's a difference of 0.47. I just calculated the difference and I put the absolute value so that I don't get negative numbers. I just want the positive difference, let's say. And you see for some of them, the fit is pretty good, like that one, there's only a difference of 0.23. But for some of them, the model doesn't really predict much. There's actually a difference of 1.63 in this case. This person is, let's say, somehow an outlier. He or she is one of the people that sleeps the most, but gets like one of the lowest grades. So if you take all these errors and you average them, so you take the mean, you see that the mean error, the mean is 0.76. So on average, your model for this data misses the true value by 0.76. Okay, which means that, you know, whatever prediction you get, you should probably adjust it by a 0.76 up or down because your model is not so precise. And in fact, this was like a weak correlation, at least for this example. I have done all this analysis with a weak correlation also to make a point here. It is okay to get a weak correlation. You don't have to look for strong correlations. It's perfectly fine to find out that something is not correlated to something else, or it's not so correlated like you expected or you hoped. Okay, so sciences are full. The sciences are full of things that we believe might be true, but then they end up not being true. So our hypothesis of a correlation between the number of hours of sleep and the results that we get in school was reasonable, but you know what we got from this analysis here told us that probably we need to change our hypothesis, or we need to somehow find other variables, or simply this hypothesis doesn't work for that group that we surveyed. Okay, so is there any question about all this and how I use GeoGebra or anything before I move to another example?
No.
Okay. All right. All right. So I will then upload this video somewhere, like on YouTube, or I will send it to you so that you have it as a reference and you can see how to use it. But maybe I will just review that. This tool here up will give you some information, especially the Pearson's coefficient. And the main thing that I did here on my spreadsheet is to select my two columns, X and Y, and then to do some two variable regression analysis from this button over here, okay? And then the window will pop up with this diagram. If you want to move the diagram on the Cartesian plane, you go here and you say copy to graphics view. This is what you get, what you need to use in order to get your line also on the Cartesian plane. And not only that, but I also, when I first put down the values here, I also created a list of points with this command here, list of points. Okay, in this way, then you will have in this first part of the window on your GeoGebra, you will have the definition of everything, in particular the function g, which has been found with this by GeoGebra automatically with this command, fit poly. Okay, so maybe I will save this one. Okay, I'm gonna call it sleep versus grade, 22 January 2021. So I remember, and I might even send you this file if I find a way to save it somewhere. There might be like a public space where all my GeoGebra stuff is published. Okay. How about we do another example in which I don't do regression analysis, but I use other functions. So new file. There we go. I am going to close everything here so that I show you again all the steps, which is good for. So when you open GeoGebra, you usually see this. There's the Cartesian plane, and there's also like a list of input lines. Like for example, I don't know, let's say I wanted to plot the function f of x equals x squared minus 1. Minus 1, that's a parabola, and here it is. Okay. I'm not going to use it, but just to show you what you can do with GeoGebra. Okay, you can intersect it with another line. You can take G to be the line, I don't know, 3x plus 1. Okay, and here you have the two graphs, and you might even want to find the intersection point. This is just to show you how fun it is to work with GeoGebra because it's very quick. You can click on intersect and find the coordinates of those two intersection points. Here we go. You have solved a system of two equations. Anyway, this was just a little digression. Okay, I don't know what's going on here. There's too much stuff. Let me go back to not having anything. There we go. So I'm going to open a spreadsheet now to do another analysis, and I'm going to copy some values from another set of data that I have here. If you don't mind, you're probably not going to see it, but you will see it on GeoGebra once I come back. There we go. Here it is, and it just goes all the way up to 9. This is time, and this is price. So I am analyzing how the price of something, I have no idea what it is, changes with respect to time. And the time is measured in years, okay, and the price is measured, let's say, in euros. So first year, something costed 23 euros, and then it went up to 25, 26, 30, 35, 45, 57, 70, and 100. For some reason, after 9 years, this price went so up to almost be quadrupled, if you think about it. I'm sorry, I cannot give you any more context. This is just an example that I made up. But okay, it's just to show you how to use GeoGebra basically to do this type of analysis. Now, if we look at these points, so we'd select them, and we go here and we make a list of points. Okay, we call it, again, list. It doesn't really matter what we call it. We can call it price. Okay, and then I move to my graph and I look for them. Obviously, because they are high, I need to somehow change my view. Here we are. So by rescaling the y-axis, I see my points here, and here they are. Okay, so what does it look like to you? What kind of function can that be? Does it look like a straight line? Can we do a linear fit, a linear regression for this? Anybody?
No, it's not a straight line.
Kind of like a straight line. Yeah, maybe the second part, I don't know. It kind of starts slow. I mean, a line is something that goes constantly up, like the increase is constant, let's say. Let me see, what else? Let's do two variable regression analysis. And the cool fact about GeoGebra is that not only does it do regression with straight lines, but with any function you want. So you see that if we choose the linear model here, which is a straight line, here's what we have. We have a fit, which is probably, again, not so good. Let me see what the Pearson coefficient is for this case. Well, it's 0.91, so not bad. It's actually pretty strong. So yeah, we can use this model. And this model will give us this line. How about we move it to the graphics view so we also see the line over there? Excellent. Now we also have the line. It's called h of x. You see over here the red function. We have it. It's 8.67 x plus 2.33. That's the line. Let's say I want to evaluate. I want to make a prediction about what the price will be on the 11th year, 97 euros. The 12th year, 106. I don't know. After 20 years, 175. And all these are predictions that you can make with your model. But again, remember, this is extrapolation. So the further you go away from your domain, which is numbers from 1 to 9, basically, and the worse your model work as a predictor. So maybe for the 11th and the 12th year, it's fine, but not so much for, I don't know, the 30th year. I have no idea. This object might not even be sold after 30 years. So the further you go away, and the worse it is. And also you could make like past predictions, like what about year 0 or year -1, which you might say, what is it? Well, you know, 1 year before you started, well, you even get negative prices, which is pretty bad. So this model clearly has some limitations. It doesn't work for predictions in the past. Let's say if I want to imagine what the price could have been before my analysis, it gives me negative prices, not good. And I don't know, I mean, for years that are very far away from my domain, it might be good or not, but we really don't know. How about we do a similar analysis as we did before? So what about the slope? Can anybody now tell me what this line is telling me in terms of slope? The slope, which is 8.67, what does it mean? Every year, complete my sentence, what do we get? On average, come on, people, I will ask my question again. If you look at the slope of this line, it's 8.67. And the slope is the ratio between how much the y increases with respect to how much the x increases. Okay, so if you take an increase in x of 1 year, then the increase in y is 8.67. It's pretty easy to interpret the slope. X increases by 1, y increases by m, by the slope. So every year there is an increase of 8.67 what? Euros. Okay, so increase 8.67 euros every year. Every year. This is what this line is telling us. Okay, for this model, the average increase in the price is 8.67, which is not true basically for any year. Look at the first year. The first year, the price went up by just 2 euros. The third and second year, between the second and the third year, it went up by just 1 euro, then 4, then 5, then 10, then 12, then 13, and then 30. So, you know, this increase is like very, very scattered and varied. I think we can also, let me see, change this into a way that, okay, well, I can see the residual. There was a way in which I could connect those points together. I don't remember where it is, options, line graph, here it is. Okay, so you see, compared to the behavior of your price, the line, to me, doesn't really show much. So it's not really a good model. Let me see what the values of the line are. My function is called x. So in the third column, I will calculate h of 1, h of 2, h of 3. Okay, so h is the name that GeoGebra is giving to this function. You see it here on the left. Okay, so if I do h of a2, it will calculate h of 1, which is 11. It's the same thing as doing here, you know, x equals 1, y equals 11. Let's say x equals 2. I will get 19.66. Let me see. I will just drag it down. Well, if you can also do like h of a3, same thing, and that's what you get. And now that you get it, I can just drag the numbers. I don't know what's going on here. I can just drag the numbers down to show them all. Okay, so these are the values of the line. I can now calculate the error or the residuals. Okay, here by taking the absolute value of, what was it? Let me see, the absolute value of B2 minus C2. B2 minus C2. There we go. So there's a difference in 12 euros between your model and the reality of the price. Okay, so for the first year, your model is definitely not good. And then we see that, you know, there are some years in which the model is good, some years in which the model is not so good. And on average, your not so goodness, let's say, whatever that means, your, you know, the goodness of this fit is that it misses your price by on average 80 euros. Okay, so probably not so good. Average error. How about we try a different model? I don't know what happened here. There's nothing anymore. Okay, fantastic. Well, let's do this again. Let's do the two variable regression analysis. There we go. And how about we change the model? Instead of having a straight line, I'm going to choose another function. And there's many possible choices. How about a polynomial? Polynomial meaning usually something like a parabola or a cubic. You see that this is probably much better. Okay, the equation of your polynomial is right there. You can copy it in your exploration and say, well, this is the parabola that best fits my points. It's not the best fit, but, you know, among all the possible parabolas, this is the one that is closest to my points. How about we use that? I also am going to copy that on the graphics view, which I can show you here. You know, it's kind of weird now, but if we rescale it a little bit like this, you can see that probably your parabola, which I would like to do in a different color. Can I? Yeah, how about we make it green, just because I like it. Okay, the parabola to me looks much better than the line in terms of fit. And in fact, if we go here, okay, and try to calculate. So I'm gonna copy these numbers again, and I'm gonna redo this analysis. Ouch, what happened? I'm gonna copy the numbers, hopefully. Let me see. And I'm gonna redo the analysis perfect here with a quadratic model. The quadratic model should be here somewhere. I found it in green. It's P of X. That's actually pretty good because P stands for parabola. It's purely by chance. But my quadratic model is called P, so I'm gonna calculate P of A15. That's the value of the parabola. You see, it's pretty close. For some reason, it's not showing there anymore. Fine. So let's see what the parabola gives me with respect to the real values. You see they're pretty close, okay? 24 over 26, 27 over 30. So the error, the absolute value of B15 minus C15, the last two columns here, 23 minus 25.85 is just 2.85. That's the difference between these two numbers. And as you see, they're much smaller. So this is definitely a much better fit than the other one. On average, this model misses the true values by 2 euros, which is much better than the previous one. So in your exploration, if you are looking for models, if you do this analysis with the residuals, okay, with the errors, like I did here, you can definitely find which one of your models is better because it gets closer to your points. Now, obviously, there's something also wrong about this parabola because, you know, probably for past predictions, it's not good. Look at the side of this parabola on the left. It kind of goes up again, and it probably doesn't make sense. The price before your analysis was even bigger, but it doesn't really matter. It depends on the context of your problem. Your X variable is time. So in this case, it might not make sense to go back in time simply because maybe the product didn't exist before you started to analyze the data. I don't know. How about we choose another model just to show you? How about the exponential? Okay, exponential seems to be okay in terms of, you know, growing, not too fast later. And it doesn't go up on the left side, so it's probably a little better than the parabola in that sense. But let me see on this graph what we have. Here on this side, we have, okay, another graph, which I'm gonna do in a different color, otherwise it doesn't really, nope, feed exp. I just want to change it to blue. Okay, so you see the blue function is an exponential function. Okay, it's different in it's 1.6, it's 16.2 e to the 0.18x. That's a different model. Okay, it's a different type of growth. You can click on the other functions to make them disappear and just keep that one. Well, we can do the analysis of that. We can do it even here. So exponential, it's called Q. So Q of A15 gives me that value. You see, it's probably not as good as the parabola. And the other values that I get here are like that. And the residuals for the exponentials are, well, I need to take the absolute value between the true value, which is in column B, B15, minus the value that I got from the exponential, which is here in column E, E15. Okay, so I did the difference between the true value and the modeled value with the exponential. And here is what I get, and the average of these numbers. And it's 4.14. So you see clearly like what we saw on our, on the graph. Our exponential function might be, going pretty close to our points, but the parabola was probably better. So the quadratic model is the one, where is it? Is the one that I would choose to model this. There we go, P of X, okay. It gets much closer to your points compared to the exponential. Now, then the exponential usually, I don't know if you can see that, if we go up and up, then there is a point in which the exponential will definitely overpass the quadratic model. That's true for exponential models in general. They usually go up to infinity, we say, much faster than the polynomials, than the parabola, for example. But in this side here, which is the one that we're looking at, the exponential seems to be like too high at the beginning and too low at some point. So in that sense, I would say it's probably not a good model, and definitely, although it's definitely better than the linear one, if you look at this, okay, because the linear model was kind of, not really a good one for this set of data. Okay, I would say I'm gonna stop the recording now because I am done with showing things with GeoGebra. I know that when I stop the recording, something might happen, that Zoom sometimes kind of crashes. So if it crashes, I'm gonna be back here and we can, spend the last 10 minutes of the lesson on Zoom anyway. So I'm gonna try to stop recording.